share screen 秀印代表 share screen 可以上问题。这个先开。这个等一下你们要用，这个你们要用，这个你们要用。金生，控制它。到了啊。2点了哎，金生，2点了啊呀，你迟到哎，这里全部人的时间，对啊，全部人的时间在这里等你在外面吧。Yeah. Okay. So next group we have elliptic curve and modular form. We'll start with Jung Hong. Okay, to tell us about elliptic curve.
Hi, I'm Junhong, and the topic I'll be presenting today is about elliptic curves. So let's go into the main table of contents for today. So the first one will be talking about the history of the elliptic curves, and then we'll move on to the introduction of the elliptic curves and also what is the behavior of elliptic curves over the rational numbers. So at the start, we look at the history of elliptic curves. It was first introduced by Diophantus in 3 AD. So the way he introduced this was in his book, Arithmetica, and there was a problem written there to divide a given number into two numbers such that their product is cubed minus its side. And from there, we'll get this equation here, which is y multiplied a minus y equals to x cubed minus x. So this is actually the current form of elliptic curves that we'll be studying today. And then later on in the 11th century, Fibonacci encountered this congruent numbers problem, where it states that a positive integer n is a congruent number if it is the area of a right angle triangle with rational side length. Or for any rational numbers a, b, c, we have that a squared plus b squared is equals to c squared, and that the area of the triangle is equal to n. So from the previous, we saw that a squared plus b squared is equals c squared. This is known as a Diophantine problem. And the solution associated is of the form y squared equals x multiplied by x minus n times x plus n, where x and y are the rational points of the triangle. And after that came along other mathematicians like Newton and Weierstrass to further generalize the form of elliptic curves. And now we see that elliptic curves plays a major role in sectors like number theory, algebraic geometry, and also cryptography. So now, moving into the introduction to elliptic curves, the first definition that we want to see is a Weierstrass equation, which gives the form y squared equals to x cubed plus ax plus b. So how do we get to this Weierstrass equation? So first look at the cubic equation over a field F, which is given by this long equation down here. And this long equation here is also known as the general Weierstrass equation. So, but how do we get from this long equation to that simplified version on top is when we consider that the characteristic of the field F does not equal to 2 or 3, then we can play around with some algebra and substitute x and y so that we can get the simplified version in the definition above. Now, moving on to the next definition, we have that for a given Weierstrass equation, it has the discriminant and J invariant given by, the discriminant is given by this -16 multiplied by 4a cubed plus 27b squared. I think it was supposed to be capital A and B. And also the J invariant would be this multiplication here divided by the discriminant. So this discriminant here guarantees that the elliptic curve is non-singular, so it doesn't have cusps or overlapping spots. And if it does equal 0, it then indicates that the curve has a singularity. So the J invariant here is to classify elliptic curves up to their isomorphism, which is that for two elliptic curves that have the same J invariant, then they are isomorphic to each other. So now with the previous two definitions, we can move on to define what an elliptic curve is. So an elliptic curve E over the field F is given by the Weierstrass equation, y squared equals x cubed plus ax plus b with some identity element O. We'll be defining this later on. And then it has the discriminant given previously, which does not equal 0, and also the J invariant given previously. So now we are able to study the points on the elliptic curves by introducing some methods from algebra and geometry. So first, we define geometrically this addition rule for the points on an elliptic curve. So let's have that. P is the first point with coordinates x1 and y1, and Q have the coordinates x2, y2. And then we choose that we have the O to be 0, 1, 0 in the projective space 2. So we chose this specifically because this will give us the infinity point that we need for our addition law later. So now we define that the addition for P plus Q would be equal to R, which is our third point. And so how do they add to each other? So the first step is to draw the line L through P and Q, and then we find the third intersection point R prime where L meets E. Then we reflect R prime across the x-axis to obtain R. So to see this better, we see that from P to Q, and then we draw the line to R prime. It's supposed to be R prime up there, and then it reflects down to R, which is P plus Q. So with that, we can now define the group law of the elliptic curve. So for distinct points P and Q, the group law of an elliptic curve over a field F is given by, if x1 does not equal x2, then for P plus Q equals R, we have the coordinates of x3 and y3 given here. So this was done by some algebraic methods, but to show you geometrically, this is what. Let's say this is an elliptic curve. So for the first part, it's then we draw the line up to somewhere, and then we reflect it to get the point R down here. So this can be shown algebraically by this. We can compute the exact points through this algebraic group law. And then for the second part, when we have that x1 equals x2, but y1 does not equals y2. So let's say Q is somewhere here. So then the line drawn between them would be a straight line down. So this would be going to the point O, which is the infinity point. Next, if P equals Q, but the Y does not equal 0. So let's say for some point here, if P equals Q here, so then we just take the tangent at that line. Just take the tangent of that line, and then we can find that it touches the elliptic curve somewhere. And for the last part, when P equals Q and Y1 equals 0, so it means you'll be here. So the same thing again, we draw the straight line, the tangent line down. We see that it goes to the point infinity. So we can say that by this group law that E is a group, but is that all to it? Is it just a simple group? So the next one would be this lemma here, where it says that E and the additive forms an abelian group with O as the identity element. So to prove this, we check the axioms for the abelian group, and we see that the identity, inverse, and commutative part can be checked trivially. However, for the associativity, we have to use the Cayley-Baccarat theorem, which states that if two cubic curves intersect in 9 distinct points, then any other cubic curve passing through 8 of those points must also pass through the 9th point. So this will show us the associativity. So how do we do this? We construct 6 lines here. So line 1 would be through P and Q, line 2 would be through O and Q plus R, and line 3, and so on. And then we see that from this table that each line intersects with E at these 3 points. So by the group law definition of X previously, because we have it that it intersects from L3 and also from M3, so it will have 2 definitions. So from L3, it will be the negative of the bracket P equals Q plus R, and also from M3, you'll get P plus the bracket of Q plus R. So since the 9 intersection points agrees on the conditions of the Cayley-Baccarat theorem, we can therefore conclude that they are equal, and then reflecting about the x-axis gives us the associativity that we wanted. However, there are some special cases where the lines are equal to each other, and these cases can be checked tediously, but in the end, we will see that the associativity holds for all cases. So now moving on, we want, because we started from the Diophantine equation, so we want to move back and check on how does this new group help us in the set of rational numbers. So before that, we introduce a simple prerequisite, which states that for an elliptic curve over a field F, a point P is called a torsion point if there exists a positive integer such that NP equals O. So this torsion group will be labeled as this, EF torsion. And then the following theorem will provide the necessary conditions for determining all these torsion points. So this theorem is called the Naegele's theorem. And for an elliptic curve over the rational numbers, if P with coordinates x, y is a torsion point, then x, y must be an integer, and also y equals to 0 with order 2, or y divides this thing that we saw from the discriminant. Right. So the sketch of proof for this theorem would be to consider p-adic valuations, and then we substitute for x and y into the main curve equation, and then from this equation here, we see that if either v1 or v2 is lesser than 0, then both must be negative with 3v1 equals to 2v2. So we then let v1 equals to negative 2v and v2 equals negative 3v for some positive number v. So the idea of this proof is then we find a contradiction so that this V does not exist, and thus X and Y must be integers. For the second part, this can be shown just using the group law formulas, which is quite true. And now moving on to the main theorem, which is the Modular theorem, which states that for an elliptic curve over the rational numbers, then the group of points of the elliptic curve is finitely generated, and it is isomorphic to this finitely generated, where R is greater than 0 is the rank of the curve, and the torsion group is finite. So a sketch of proof for this would be to prove the weaker version of this theorem, which states that the subgroup here is finite. So this is the most technical part of the proof, which uses things like Selmer group, Page, Safarevich group, Kummer theory, and also Galois cohomology. And then the next step would be to introduce a height function, which would lift this weaker theorem to the original one. And also, it will control the number of generators to make it a finitely generated group. And also the last part would be to apply the previous Nagel-Lutz to find the finite torsion subgroup. So now linking back to the initial motivation, we are now able to predict whether for the congruent number problem, whether there are infinitely many solutions or not. So it is found that all these type of Diophantine equations tend to have an associated elliptic curve. So this can be seen in the Fermat's last theorem, which states that no positive integers a, b, and c satisfy the equation an plus bn equals cn for any integer n greater than 2. So how is elliptic curve used here? This was by introducing a special type of elliptic curve called the Frey curve. And then they combined it with modular form to show that no such elliptic curves exist, and therefore having the proof. So yeah, that's all I have. But yeah. Let's try to classify the curves using J. Oh, I think for the J invariance, I think later on for the proof, I think for the modularity theorem, it will be important to classify the elliptic curves that are isomorphic to each other to be the same, so that they are like there are lesser things to study. I think this spring. Let's see. I'm not sure. Um, I think
So points in the elliptic curve based on Q, they form a group. Some of the elements of the group their orders are finite, like maybe like 5p will equals flexible. And some of them they have in some of the elements though they have like infinite amount, their order is infinite. So the length of the curve is the number of infinite order elements. You can see it was quite large. Yeah. Of course, we're talking about rational points. Rational points on a curve is indeed infinite. So the z to the power of r, the r is the number of infinite generators that are in the group.
Okay, so basically this isomorphism just split the point into infinite order and torsion.
Yeah, torsion means those are the finite order. Yeah, but an interesting thing about this elliptic curve is that those that are infinite order are not unique. So maybe like you will have this set of infinite curve that does not equal to that set of this set of generators does not equal to that set of generators, but both they can generate the same thing. The thing that is consistent is that we can at most find R amount of infinite generators in the elliptic curve. So that's why it's defined like this.
Wait. So R is the number of generators.
Number of infinite generators.
Number
the infinite order generators.
Yeah, generators for the
For
set of
the group of the elliptic curve.
generator for the set of elements with infinite order. But how do you know that they form a free group? Why are they forming a free group? It's not free, I think not free, right? Because you generator meaning you like reduce by
It's not necessarily free. It's not necessarily free. So this theorem says that you can find R elements that are free that can be presented like this. That is this theorem is about.
process isomorphism, group isomorphism.
Group isomorphism.
But in this case, you say that then it is freely generated by zero.
That means that
But just now,
meaning it can decompose into a free part and a portion.
but just now it says that the free part generate the infinite order.
Yeah. Free part generates all the infinite order elements. Technically, there are infinity infinite order elements, but you can find R of them that generates all of them.
Okay, I think.
Example we see in the textbook, they are usually like 10 digits of numerators and denominators. So number, it is usually not trivial.
Sorry.
What is it like split into two types of generator?
Infinite and finite. Yeah.
Oh, so the generators for the
All the infinite orders element group can be generated by R elements component.
and all things.
Technically no, because the same PQ 就到最后就变成这个样子，你不能这样讲，因为你哪一个 Z， 你哪一个 infinite 的乘一个 finite 的，它又是一个 infinite 的funktion。所以
So if the group is z plus z by 2, then z plus z by 2, so it's z plus z group 2 elements. Then the element 1, 1 can generate is infinite order also.
while the elliptic curve, the curve will be isomorphic to the group, but the points will not be equal because EQ, all the points in EQ should 需要满足那个 elliptic curve 的那个函数 should satisfy the equation the y squared equals x cubed plus ax plus b to satisfy this condition. So you can say that there are the group is isomorphic to, let's say, z plus z equal 2, but the points in it will not exactly be those points. You just can find a generator, an infinite generator, and another element of order 2, and then you look at all the rational points. You can combine it all from this.
And I think the issue is only that you said that just now that every element of infinite order can be generated only from the set.
Yeah. That's actually wrong. That is actually wrong because technically you can multiply an infinite order and a finite order, and you still get an infinite order. Because that tells it, given say that it is isomorphic to such a this thing.
Okay, thank you.
How to present? Okay. So hello everyone. My name is Li Hao Tian, student ID MAT 2309814. And today I am going to continue on the presentation on elliptic curves. First of all, I would say that one of the application of the elliptic curve, which is on cryptography. Then I will introduce lattices, which was spoken by the first team. It talked about lattices and toruses. I will speak about that, and then we will show you how does the elliptic curve, when defined over C, over the complex plane, is actually isomorphic to lattice. Okay, first have a quick refresher. So elliptic curves, almost all of them, you can simplify them to such an equation: E equals to y squared. E is y squared equals to x squared plus ax plus b with the discriminant as this one. And it was a smooth projective curve with genus 1, which means that you have one hole, with the identity is the point at infinity. Okay, so we have learned about the group laws. Points in this curve forms a group, an abelian group. No matter if you define it on finite field, on rational numbers, or even on real numbers, each of them forms a group. Okay, so now we start talking about cryptography. The key in cryptography is a hard inverse problem. It is easy if you get from A to B, but when you reverse it, it is extremely hard. One of the most used cryptography, the RSA, use the factorization problem. You take two large primes, multiply them together. This is simple. We can all do this in basic math. We have learned about it. But if you take the result, and if I ask what is the two numbers that I ask you to factorize this large number, it will be very, very hard. So that is the key in the RSA. So in elliptic curve, we have a similar question called the elliptic curve discrete logarithm problem. Okay, the point is this: we know that each point in an elliptic curve, they act as a group. So we can multiply like 5, we can multiply like k, which means that p plus p plus p plus p plus 4 times to get 4p. So given a k, an integer k, if we want to calculate kp, there is actually a fast algorithm for it. First, we take p, and then we add p to p, we get 2p. We add 2p to 2p again, we get 4p, and then we continue on. And then we will get p, 2p, 4p, and then to the power of np. We take all this, combine, pick those that we need, and then add it to our number. For example, if we need 7p, we just add p plus 2p plus 4p. This will give us an O log n method to get to the number, to get to the point kp. But on the inverse problem, if I give you q, I don't even give you k, I just ask like what number can multiply itself to become q. This question is hard, and it is the current fastest algorithm takes all square root of n. And this problem is actually much more effective than RSA, means that the easiness from one direction compared to the hardness from the other, this is actually a lot more significant. For an example of what I am talking about, imagine we take an elliptic curve defined on the finite field of 97. It's y squared plus x cubed plus 2x plus 7. So let's say me and you, teacher. So we have decided to use the base point p, which is 446. It is a point of order 15. So first, let's say I choose 7. I multiply 7 times p. I take it out, 6895. The teacher might choose 11. He multiply 11 to this point, he get 8596. And then once I get your number, once you get my number, we multiply the number with the number that we have on our hands. Alice takes b multiplied by 7. Bob takes a multiplied by 11. And then both of us will get the 9258, which is a shared secret among us that the other people, when no matter even if this information was hijacked, they cannot know. So this shared secret will then be used as a cipher for whatever message that we will send. This will make it safe. So why do we even need to use elliptic curves when we have a simple RSA? Why need to learn all this? Because elliptic curve is actually much more efficient than RSA. It means that it takes less memory, it takes less bit, and it takes less computing time. It makes a very useful thing to use it on phone, which has limited space, limited electricity, and all of that. So all of the mobile banking apps, all of the Bitcoins, they actually use ECC, elliptic curve cryptography. So this is one of the usage of elliptic curve cryptography in our everyday life. Now to the next section. We were switching fields from a finite field to the complex plane. Before we talk about elliptic curves on complex plane, though, we need to talk about lattice first. So what is a lattice? Imagine if I give you a complex plane and I just give you two vectors, two complex numbers, omega 1, omega 2. Let's say omega 1 is 0.5 plus 1.5i. Omega 2 is 1.5i plus 1.5i. And then we consider all the points that are generated by these two vectors. We will get a lattice, more like a grid, but not exactly a square grid. Also, so this kind of thing is called lattice. So once we have defined a lattice, we can define the quotient of the complex plane on the lattice. Well, the lattice is a group. It is a group. You can define addition and subtraction on it. So once you quotient it by the lattice, we will form a quotient group. Points in it will be equals to points on the complex plane plus the points of the lattice as the mod. So if we consider the unique elements in this quotient, it will be on a parallelogram. We call this parallelogram, the fundamental parallelogram. All points in this quotient group, you can see it as it sits in this parallelogram. And you can imagine that if you move from the left side, you eventually reach the point where it is equivalent to the right side. If you move up, you will eventually reach a point which is equivalent to those that are down. So this parallelogram is actually a torus. What is a torus? A torus is a thing that is a space that is topologically equivalent to, let's say, a donut. So if a way to see this clearly is to imagine this parallelogram. Since when I move to the left, it comes from the right. When I move from the up, it comes from down. You can imagine if this has this square, you fold it, connect the sides, and then you fold it again. It will do form a torus. So this shape, this parallelogram, in this structure is actually equivalent to a torus. How it is equivalent, we will show it later. That is part of our talk. So now, I ask a question: when are the two lattices identical? Because the lattice points are the points on the plane, you can actually take two different generators, two different omega 1 and omega 2, and reach the same lattice. So I won't prove it, but it's actually quite intuitive. Omega 1, omega 2 with omega 1 prime, omega 2 prime, they are equivalent when you can present them each other by adding them with integer coefficients. Means 5 omega 1 plus 2 omega 2 equals omega 1 prime. Convert into linear algebra, it says that we need to have a matrix which is an integer matrix and it is invertible. Because you cannot only have the first represent the second also need to represent the first. You need to be able to invert the integer matrix back to the other side. So this is an example. These are the two different omega 1s and omega 2, but they form the exact same lattice. Another thing about the quotient, another thing about this quotient. So when we're talking about the fundamental parallelogram, the quotient of the complex plane, there is a proposition. So when the complex plane quotient by L, lattice L, and compared to the complex plane that is quotient by lattice L prime, there is a complex analytic isomorphism. What is complex analytic isomorphism? Just the complex analysis class. You can differentiate it. It's analytic, it's isomorphic. That's the same definition. There is a complex analytic isomorphism between the two, if and only if the lattice they have a relation. You can multiply one of the lattice is actually equal to the other lattice multiplied by a complex number. Why is it so? I won't prove it here, but I will just say the reason. And all of the entire automorphism of C means the thing that map all of the complex number to the whole complex number isomorphic. There is only one case, AZ plus B. All other cases, they have poles, they have repeated, it is not bijective. This is the only case where it is an entire isomorphism between the whole complex plane. So once we quotient it by a lattice L, we actually took care of a translation part. So all that remains is that when L prime equals to AL, C quotient by L is isomorphic to C quotient by L prime. Combining these two propositions, we now have this corollary. Given two lattices, L and L prime, the complex plane quotient by L is isomorphic to the complex plane quotient by L prime. Analytically means that the function that maps between them is a complex analytic function if and only if there exists an complex number A and a matrix in the special linear group of integers such that this equation, it satisfies this equation. So this is okay. So I have now walked through the basics of the lattice and the complex torus. We'll now ask. Oh, there's one more thing. Reduce to the canonical lattice. So now we have a lot of isomorphism between lattices. This lattice might isomorphic to that lattice. So if we want to simplify them, we can actually simplify all of the lattice into I tau, where tau is a complex number in the upper half plane, the upper half plane of the complex plane. So given two complex number, tau and tau prime, tau is only the complex torus is only isomorphic to each other if and only if tau prime is equal to A tau plus B divided by C tau plus D, with A, B, C, D is in the special linear group. This can actually be proven by using the corollary above with some linear algebra. You can prove it in exercise, but I won't prove it here. For example, the example that I have posted just now, 0.5 plus 1.5i, 1.5 plus 1.5i. This lattice is actually isomorphic. The complex Tori related to this is actually isomorphic to when tau is a third plus a third I, which is on the upper half plane. Okay. Now we try to define functions on the fundamental parallelogram. We call those elliptic functions. So functions in this, no, I'll just draw it. So functions in this parallelogram need to satisfy an important characteristic, is that the value of this point needs to be equal to the value of this point. Since we are defining it on the quotient of the complex plane, on the complex torus. So we call those functions elliptic functions. Written it down, we call a meromorphic function, which is basically just a holomorphic function except for a few points. A meromorphic function f is elliptic. It's called an elliptic function if fz plus omega is equal to fz, where the omega is point on the lattice, which means that you can move it according to the lattice point and it will still remain the same value. We can denote a field of all such functions as CL. L is the lattice that we are interested in. And the fundamental domain of this kind of function is the fundamental parallelogram. An example, the most important example for an elliptic function is the Weierstrass P function. A Weierstrass P function is, well, it is just, I won't speak it out. It was just this thing. Okay. So this series is actually absolute convergent. You don't need to try and just on every lattice point it have a double pole and it is absolute convergent. So to dive deeper in this function, before that we need to talk about the Eisenstein series, which is another series. Each of the k is an absolute convergent series. So let's say that if we define a lattice L and we define a lattice K, each of the term is they are actually just a number. You can just get the number by summing all of this together. Okay, so with Weierstrass P function and Eisenstein series, now we move to the next proposition. So if we try to find the Laurent function, the Laurent expansion of the Weierstrass P function, do guys still remember the Laurent expansion? It is Taylor expansion, but you can put the z on the denominator. So if we find the Laurent series of this function, we will get this thing with G2k plus 2 is an value that we can get from the Eisenstein series. So once we get this, we will notice that it actually is this Weierstrass P function actually satisfies this differential equation. But this differential equation is an elliptic function, is an elliptic curve. X squared minus ax minus b. So now we have an interesting function. This function, once you have chosen the lattice, it takes a z from the fundamental domain, from the fundamental parallelogram, and then it can map to a point in that elliptic curve. Okay. So turns out that this mapping is actually a complex analytic isomorphism, and it is also actually group isomorphism. And then we call that a uniformization theorem, which means that using this Weierstrass P function, we can actually take points from the upper half plane and then use the points in upper half plane, define a lattice through it, and use the lattice and then define equivalence class for the elliptic function. This is called the uniformization theorem. And the consequence of the uniformization theorem is that there is a bijection between the complex torus and the equivalence class of an elliptic curve. Remember that this mapping, the Weierstrass P function, it also maintains the group law. Means that the addition in this parallelogram maps to the group law in the elliptic curve. This is a very important property. So if we want to go beyond the uniformization, we will notice a problem. Let's say CL, we say the CL. There are actually things that are isomorphic to CL, as we have said before. So if we move in further, we can define the points in the upper half plane by equivalence we will call the modular equivalence. Modular equivalence, tau prime equals a tau plus tau equals to tau prime if they satisfy this function. And then using this equivalence, we will, let's let gamma 1 be the special linear group. And then we can define y as the upper half plane quotient by the equivalent class of this special linear group. This actually forms an equivalent class. So that each equivalent class corresponds to an equivalence class of an elliptic curve. Furthermore, we will notice that the special linear group is actually generated by these two elements. One of them is to make z to 1 over z negative. The other is to translate it by 1. Combining these two, we can actually get the fundamental domain for the value for the modular equivalence. The fundamental domain, every point in this fundamental domain actually signifies one type of equivalence of elliptic curves in the when we define it in the complex numbers. So now we have this is the conclusion given complex number using the modular equivalence, we can use it to represent an isomorphism class of elliptic curves. And that is all I'm presenting. Thank you. SLN.
Yeah, this one. Are you touching the line? If you touch the line.
Okay, I'll try not to touch it. Okay.
So you said that two lattice are equal using. Just now you just say that M need to be invertible, right?
Yeah, and need to be invertible. It needs to be integer coefficient and it needs to be invertible. So then combining these two, we just need special linear group of integers.
So you make sure the determinant is one that is.
Well, it has to be.
But your Z is already integer.
Yeah, Z is already integer. So if M is not invertible, if you just put integers inside, then you can represent you can present one of it by the other, but you cannot represent the other two.
I think my problem is that it's
Well, if the determinant does not equal to 1, you need to be able to multiply like 1/2.
you mean when you take the inverse.
Yeah, when I take the inverse, you need to multiply 1/2 or 1/3, and then that will make it not representable by the other lattice.
So does this SL2 correspond to the SL2 in modular?
Yes, actually. So that is the next person's part, which it will say it will not touch elliptic curve. It will straight up start from modular equivalence. Modular form is actually defining functions using modular equivalence. So let's say the function that reflects this one, if f tau equals to f tau prime plus some of the stuff, that is actually we call modular functions that respects the modular equivalence, modular forms, which is the next part of the talk. This one? Upper half plane, this one. Yeah.
Is there anything particularly special about these regions that are open above?
Anything particularly special about these ones?
All the regions, those are open above. Does it say anything different about those?
If there is a difference in the next chapter modular curve, you will notice that we actually need to define an infinity point for this one. That's the only difference. That's the only difference. For this one, for points of here, we don't need to. This part is already compact, but for this one to be compact, we actually need to define another point of infinity. And other than that, there is no difference. They're actually the same. Wait, I have a mic. OK， 那还是我的，这个还是我。
Modular forms have, at first
Okay, so that is problem with our third presenter. So there will be no beamer slides. I will try to pick all the points that he will speak. So before I write things on, everybody please enjoy this video. For now.
Modular forms have, at first glance, nothing to do with elliptic curves. Here's the definition. A modular form is a smooth function f from h to the complex numbers, where h is the upper half space, the set of all complex numbers with positive imaginary part. This function has to satisfy a bunch of properties. First, a technical condition.
Okay,
as
so
in
that's one with the
f.
sound, so
Fine, so okay, I think.
From h to the complex number.
那边最大。
numbers, where h is the upper half space, the set of all complex numbers with positive imaginary part. This function has to satisfy a bunch of properties. First, a technical condition. As mz goes to infinity, f stays bounded. More importantly, it satisfies a so-called modularity condition. To see this, let's notice that this function has a few symmetries. It has translational symmetry. It repeats along every strip. It has reflectional symmetry. It has fractal symmetry. It repeats itself as you zoom in. We encode symmetry using group theory. Now, this is going to get really formal, so buckle up. Let's define a group SL2Z, the set of all 2x2 matrices with integer entries and determinant 1. SL stands for special linear group. We'll allow elements of the group to act on complex numbers. For any complex number z, define ABCD acting on z. Now here comes the point. Let's require that for every matrix A in the group, f of AZ equals f of z. The intuition is that f doesn't change under the different symmetries of the group, except
Okay.
So
Wait, wait. Yeah.
elliptic curves. We saw earlier that the epsilon ends can label an elliptic curve. Likewise, we want to label a modular form with a C.
it's actually over.
Yeah.
It's actually over. I just need to play the modular form until the modularity theorem. Okay, so the sound quality may be a bit disappointing, but I believe that everybody sees that everybody have some sort of an idea. So I'll start from where I left, where the last presentation is left. So we have defined if gamma 1 is equals to the special linear group of Z, we take the upper half plane quotient by the equivalent class decided by gamma 1, we call this Y1 equivalence class. But as I have just said, it is not compact. So we actually, to make it compact, we need to add another point inside. Q all of the rational numbers to infinity, which is, if you draw the plane, is actually this point. So why all these points? Because actually all of these points are in the same equivalent class. So technically we are just adding 1 point. All these points are in the same equivalent class. So let's call it H star for the points that are in the points of the upper half plane plus these points. Okay, now we define x1 equals to H star quotient by gamma 1, which is the same equivalence class as before. The A tau plus D divided by C tau plus D is equivalent to tau. So we call this a modular curve of level 1. Instead of modular curve of level 1, there are actually modular curves of, well, all kinds. By choosing different gamma 1 means that if we consider different kinds of equivalent class, we can actually get different equivalent classes. For example, the most used case gamma 0 and gamma 1 and gamma 2 and are written down by like this. They are almost the same, except for they are also still in the special linear group, which A, B, C, D are integers. But the difference is that the A, B, C, D, sometimes they consider it 0 or 1 by mod n, modding by the level. So each of these, when we consider the upper half plane quotient by them, we will get different equivalent classes. These different equivalent classes, they are called modular curves. Why use curves? Why not call modular equivalence? Because by something called Gaga principle, all Riemann compact surfaces are isomorphic to a smooth projective curve in C. And somehow, these equivalent classes, they are Riemann complex surfaces, which X1 is actually called something called a Riemann sphere. I'm not sure what it is. So, just a sphere. Okay, so if I know that earlier, I might be able to take the proof and say something interesting, but not today. So all of these different equivalent classes, they are called modular curves. So now, what is a modular form? Just as now, modular form is a function with respect to these equivalent classes. When are they used? Whenever you want something about these equivalent classes, you will use modular forms. So a modular form, it can be written like this. Fz will be equals to Fmz, M is a matrix, with Cz plus d to the power of k, where k is, we call k the weight, and then we call the n the level. The level of the modular curve it is defined on. You can say that a modular form actually takes value from the complex plane, which is why it looks so complicated. But if you restrict the input from the respective modular curve, it is actually just a simple one-to-one function. It except for this weight. So later on, when we talk about modular form, we will specifically use something called a cusp form. So what is a cusp form? Cusp form is just modular form. It vanishes at its cusp. And all of the cusp points are basically this point that had been adjoined to the upper half planes. So if a modular form that reached 0 at its cusp, it is called a cusp form. And one more thing. All modular forms can have a Fourier series. Modular forms can be expanded to a Fourier series. So the Fz here could actually be written as n equals 0 to infinity an, which an was in C, plus e to the 2 pi I sec n. All modular forms, they have a Fourier expansion like this. And that is everything about modular forms. And thank you.
This appear in the.
You mean that will I type out this report? No.
I mean, like, type out like whatever you know here. Is it possible?
Yeah, it is possible.
Yeah, you don't need to like write a long thing. So, because you need it like.
Yeah, need it for the next one. They will use cusp form. They will use modular form. They will say something about levels. Okay. It will be late. The report will be late. I will finish my class study first. After then, I'll do it.
The report is due.
I'll try. I'll try to make another report on this.
No need to another report, just include it into your.
Include into my report.
Yeah. And then just put whatever you know. I don't need to like go into depth into this. I know it's not your stuff, but since you already like have an idea about what is going on, then why not just jot it down?
Okay.
Yeah. Okay. Yeah. So it's like extra thing inside.
That can be done. The Fourier expansion. Is it unique? Well, I'm not sure actually. I believe it is, because all Fourier expansions should be unique since they are on different cycles. So if you put different AN, it will show up eventually. The modular, all of these modular curves, they are actually isomorphic to a smooth projective curve in total complex plane. That's why I introduced this, because the name is very confusing. Actually, for easier studying, it should be called modular equivalence class. But since it was isomorphic to a curve, we call it modular curve. But now it's already called modular curve. If I don't write this down, this whole thing might be too easy to forget.
What is it called?
Any more questions? Just by definition, it is over all positive integers, including zero. But on actual using, you just see that there is no modular curve of 1, there is no modular curve of 3, there is no modular curve of 5. So by definition, it can actually be all positive integers, including zero. But on practice, I am not sure does all kind of weight is impossible. Maybe there is maybe that 103, there might be some possible modular form. I'm not sure. Any more questions? Okay, then I pass this booth to the next speaker. Yeah, I cannot.
You just go. Oh, if you want to pick the
Okay.
then to pick the next.
Okay, modular.
Next one. Yeah, this one.
Hello, my name is Jing. Today, I want to introduce about the modularity theorem. Yes, I just most of the part was presented by Altian. I just go through the example to see what can we keep the idea. Let's see. Uh, even the elliptic curve of the field Q, to solve the Fermat's theorem, we actually need to see the solution for the free curve. This is the y squared equals to x times x minus a to the power p plus x plus b to the power p. Where a to the power p plus b to the power p satisfy the equation, famous equation, which is equals to c to the power p. Now we ask a more general equation: how many rational points are satisfied for this equation? Unfortunately, there are infinite points we want to check. However, if we if we move the study into the finite field, then we actually need to check finite points only. As the field P has a size characteristic P plus 1, and so we can consider the formula like this, which is the solution is P plus 1 minus the error integer. Here it has an error. You can see what it makes sense like this, because not too perfect for every additive curve. Yeah. We denote this equation as APE. is shown below. This is a solution of elliptic curve. Now we consider the example y squared equals to x to the power q plus 2x plus 5. When p equals to 5, infinity and the origin are the solution, as the elliptic curve is in the projective space, so it include the infinity. So the error integer is given by -4. You can see the calculation here. Next, when p is equals to 7, there are 7 solutions here. The error integer is given by 3. Given 3. When p equals to 11, we have 9 solutions here. So the error integer is given as 6. Yeah. So when we plug out the solution, when given the prime p and e, we see that they can be bound by the curve y squared equals to 4p, the red curve you see in the figure. And in general, we could this is a theorem. This has a theorem here. It is called Husserl's theorem. When you're given the elliptic curve on the finite field fp, we denote this elliptic for simplification. We just write it as E plus p fp. So here is a bound for the old solution of solution of elliptic curve. To see to see the connection between this butter elliptic curve with this butter property and modular form, we study its property. There is not curves and smooth. When given, recall the standard equation of elliptic curve is called Weierstrass equation. It's a simplification of the original equation that Junhong's present before. If characteristic f is not equals to 2 or 3. At table that doesn't include the 3 here. So this is minimal discriminant is equals to -16 times 4 times a to the power 3 plus 27 b to the power 2. And the modular invariance here is given by this formula. Yeah, it's very important coefficient. I think so. Right, and so then the proposition can be followed here. For any Weierstrass equation, is smooth only if the discriminant is not equal to 0, and it has a not only if the discriminant and the C4 is not equal to 0. Yeah, and it has a curve only if the discriminant equals to C4 equals to 0. The first part you can see is very smooth, and the second part is looks like X, but this figure doesn't show up. It's X because later we will see the terminology is called multiplication reduction. Yeah, and the third is a curve. Very obvious to differentiate. Yeah. Now, by the theorem reduction of modular P from the Junhong's project, we can is a connection between the reduction and the smooth, as we present before. These 3 properties of the elliptic curve, they are the connection. Now we use this connection to get a lemma here. If E is an elliptic curve with this
discriminant and modular invariant C4, then for any prime P, E has a group reduction at P if P is not divided by the discriminant, or E has a multiplied reduction if P is a divide discriminant and P not divides C4. And finally, E has a additive reduction FP if P divides discriminant and divides C4. That's it, and that's it. Okay. No, it's a theorem. Follow from the theorem. Follow from the theorem reduction. Good reduction is represent is a smooth curve. When given the prime P, given prime P is smooth as the curve. There are a lot of example. There are example. Later we see the example. The curve has a when it has a good reduction, when it has a bad reduction. Later we see it. Okay, additive reduction and multiplicative reduction can be combined to say as a word reduction. Now we give example for the previous lemma. We see we denote E1 to the E1, E2, E3 as we there are different property we have shown before. The first curve is a smooth curve. The second is has a knot, and third curve has a curve. So we just calculate its discriminant and C4 and get how when they have the good reduction, multiplicative reduction, and additive reduction. And as we can see, E1 has a good reduction if P is not equals to 2, 3, 5. And he has a multiplicative reduction if P equals to 5. Additive reduction P equals to 2 and 3. Next two, the curve follows like follows by the lemma we get before. It's just some calculation. So we go to the next part. Okay. Then we can see, Then we can see the conductor. Then we can use the conductor. Then the conductor can be shown here. The conductor is Then now we can talk about the conductor. Conductor is a multiplication of the all prime numbers with the discriminant can be divided by the prime number here. Recall in the Greenhouse project, if E has a good reduction at P, Fp equals to 0. If E has a multiplicative reduction, then we have Fp equals to 1. There's a power of the P. And next is if E has a additive reduction at P, then we get that Fp is greater or equal to 2. There's a calculation we can get from elliptic curves. If we calculate the discriminant, then we can get the conductor. This conductor is come from the website LMFDB. It has details about the elliptic curves and its modular form. And that's it. Yeah. 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 Now we going through some metric here is connect to the modular form. Next, we want to consider the congruent subgroup gamma gamma n, which is a spatial linear group, which is a subgroup of spatial linear group that satisfy the third entries as congruence to 0 when modular n. So the theorem is the theorem comes through a modular form of K for the gamma for the congruent subgroup is a function f. F satisfies the modularity condition and is the first one. And second one, he is a meromorphic on the upper half plane. And third, he says it is meromorphic at all curves on the modular curve. And it vanishes all curves in the modular curve. And we call it modular form. We call it curve form. Where H star is a complete complex space, a complex plane. Now we want to consider. Now we define the S2 of the subgroup of a congruent subgroup to get to contain this curve form. This is a space. This is space. Indeed, this space can be divided into two subspace. We get the notation. The operation is direct sum. Here, we see the word here has new and o. The new subspace here is a subspace that stay orthogonal to the old subspace. Literally, the new subspace contain the new form, while the old subspace, this typo here, contains the old form. Rightly speaking, the first form f is O, meaning that we can scale all the fz for some d bigger than 1, such that the d divides n. More concretely, there exists a level n. The level here is the integer less than less than n. They can divide n such that n times d divides n. To get the fdz, you can imagine that we can copy if f is O, then we can copy it using the d using the some integer bigger than 0. Otherwise, it is called new form, meaning that it's non-constructible for any d. To see the example, we first introduced the theorem. It's a theorem for it's a theorem that talk about the Fourier expansion of the modular form. Then the congruent subgroup less than the spatial linear group. Then consider the transition matrix for some positive integer h, and let h be the upper half space. Suppose this f from the upper half space is supposed to be see here. Yes, I'm going to refer here. First condition is have to satisfy the modularity condition. Second is meromorphic on the upper half space. So for any m here, as we saw in the video before, so this modular form must be must have a Fourier Fourier expansion. This has a typo here, but it's just a cycle for every coefficient. Yeah. Next, for convenient, the typo is here. It's supposed to 2 pi I h here, no divided by h. Yeah, for convenience, we denote the Fn tau equals to F tau. This shows every curve form emits a Fourier series. Because all curve forms follows this all condition, and we can get its Fourier series. Now we can go through the example. Consider the elliptic curve y squared equals to x cubed plus x. It has a conductor 32. It is a product of prime and corresponds to the following wave 2 new form in the new subspace when the conductor is 32. So we can get the equation like this. Is a Fourier expansion. Well, I claim that this Fez is non-constructible. So the explicit calculation is shown below. Yeah, when the level m is 1, we got no cos form because this space is 0. This space is 0. 2 is same, 4 also same, 8 also same. And when we get to 16, we substitute 16 to the equation, then we get 1. But we go through to M32, so we such that let D equals to 2, such that F16 substitute 2Z. It doesn't match FEZ. So FEZ is a new form. Yeah. Next, we can go through the modularity theorem. Let E be the curve over the Q with conductor N. Then there exists some new form as in this subspace. They have the equality with their Fourier coefficient and the solution of the elliptic curve. This is what the previous video says. It's a sequence like this. So this is a table for their Fourier expansion. Yeah. So you need to some practice to see what can come follow. Here, when we substitute, when we calculate p equals to 5, and we get the error of the integer is equals to 7, and then this implies the solution of the elliptic curve is -2. So they match the second coefficient for the E1. As you can see here. And the second has a -2, also the same. We can check back, it has a -2. And third is not like the same, but by supposed to be +2 because due to the twist. What do we mean twist here is because E2 because E3 behaves like the E2, so they can get the technical part to show this can match. So this can match. This is a visualization for this three curve. I don't know how to connect to the original elliptic curve part, but observe there maybe has a hole there from the first for the first part, we can see have maybe get to the hole like that, and the second has a very more too many holes there, like the black hole like that, and the third has a also the same converts to the upper half, and yeah, and as the video we see before, is some connection because the modular form has because the modular form has very like this, yeah. And this now I just play the video for you and see the connection to. Huh? How long is the video? Oh yeah.
How long is the
Just 1 minute. Yeah. Yeah. Okay.
现在进去的报纸还没准备好，其实。
哦，这样我找一下。
你有吗？
我再找一下。呃，
还是什么？
对啊，还有一个这个，这是这个，这个哦呀，about 1 minute，yeah, I just see some. As you can see here,
15调2倍，要不要？
yeah, this original modular form, and because he has a periodic, right? So when we go from the first part, then we'll go the same. We will go the same. So they consider the ball like the circle like this. A circle like this. They consider one circle for this. So we go through the next modular form, then we just go around. Just go around, and that's it. Yep. Yep. Yeah. Yeah. Oh shit. Sorry.
The hill or the S2 forms tend to be orthogonal.
I think it's linear algebra stuff. I think maybe because I'm not quite sure what is going on for this space. Because it's very related to the modular curve. I don't go deep to the modular curve. Do you mean how to recognize the difference of the new form and old form? Do you mean like this? Oh, old form is when we substitute the f when we substitute the d to the fj. I mean fj to the fdj, then it can come to the element of another level of this space. I mean in sense for using this example, Fg when you substitute 4 into this, then it can be the element in the S232. I mean, yeah. If it's a new form, then it doesn't exist for any level. The space with the other level, it's just that group. It's just that space contains it. And that's what I learned. Yeah, that's how. Okay. Any question? Yeah. Yeah. Well,
Okay, so good afternoon, everyone. I'm Cao. Today I'm going to talk about a little about Fermat's theorem. This problem has been unproven for over 350 years. Many mathematicians strive for solving this without success. So without further ado, let's see some basic definitions first. Just like Junhong's defined, we say an elliptic curve is given by the Weierstrass equation, y squared equals to x squared plus x cubed plus ax plus b, for 4a cubed plus 27b squared is not 0. And we say elliptic curve is semi-stable if its reduction modulo at modulo every prime p is good reduction or multiplicative reduction. The next is about its conductor and the level of it. I'm sure you already see it before. Next, we will consider a special modular form. We denote the space of the cusp form of V2 as the S2 gamma 02. And the gamma 02 is a matrix set. And the for the holomorphic function f, it should satisfy the following two properties. Then you might be curious about how do we define the x02. Actually, it is a compact Riemann surface defined like this. And the special thing is about this is its genus gx02 is 0. So after knowing that, we should define a general equation for the dimension of S2 gamma n and between and the x0n. So the equation is given as follows. Especially when n equals to 2, the dimension of the S2 gamma 02 is n. Remember this equality later. It will play a important role in the proof of FLT. So now let's move to the free curve. But before that, let's see a conjecture called the Ship-Ross conjecture. Actually, it is still remain unproven because some proof of the Ship-Ross is not accepted by the academic field. But at least this conjecture is true for the semi-stable elliptic curves and the free curve. It states that for every epsilon greater than 0, there exists a number C such that the absolute value of the discriminant of an elliptic curve E is less than or equal to the C times n to the power of 6 plus epsilon, and n is the conductor of this elliptic curves. Then let's define the free curve. Free curve, we have two different ways to define it, but actually they are equivalent. One is shown in the PPT, and the other one is you can just substitute the a to the power p and the b to the power p by the minus a to the power p and the minus b to the power p. Actually, they are the same. Next, so without loss of generality, we use the first one to define the free curve, and we assume the ABC are pairwisely co-prime. This implies that A is congruent to -1 modulo 4 and B is an even number. So based on the mathematician's proof, we have the following propositions. You can find the conductor of the free curve and this minimal discriminant of this free curve. So actually, free curve is a strange curve. So why is that? Because based on the Shapiros's conjecture, it says that the minimal discriminant should be close to the conductor of the elliptic curve. But actually, for sufficiently large prime number p, this might not hold. So this leads to the mathematician to get sculpture that this elliptic curve does not exist. Later, next we will go through some definition about Galois representation, but we won't go further because we just stayed at the definition. Just knowing how do we define them is enough. We say Galois representation is finite flight at every prime p if it arises from a finite flat group scheme over Z more p. And we say it is irreducible if there is no one-dimensional invariant subspace. We say the Galois representation is unramified if its inertial group is contained in the kernel of this representation. For the inertial group, it is a normal subgroup and of the decomposition group, and the quotient group determined by it is isomorphic to the corresponding Galois group over a residual field. So here is a proposition to help us how to define it, whether it is unramified. For an odd representation, we say it is odd if the determinant of the rho C is -1. Here C is the conjugation number generating the Galois representation. And for the residual representation, we define it as follows. Then based on these definitions, we can have this theorem for the free curve E and the E0. And we assume further that A is congruent to -1 modulo 4, and B is an even number. The p-adic residual Gauss representation of the free curve is absolutely irreducible and odd, and unramified outside 2p and flat and p. So next part is about modularity theorem and Ribet theorem. This is one version of the modularity theorem. And in short words, it says that every elliptic curve over few Q is modular. And based on this, Wells proved another stronger theorem. That is, every semi-stable over Q is modular. Next is about the Ribet theorem. Because I found too many versions of the Ribet theorem, so here I provide two of them. One says that let F be a way-2 uniform of conductor in L, where L is do not divide N is a prime number, and suppose the residual representation of F is absolutely irreducible, and one of the following is true. Then we can conclude that there is another new form G of way2 of conductor N such that they are the residual Gauss representation are isomorphic. The other we call it as a Ribet level lowering theorem. It states that for a prime number L, let delta be the minimal discriminant of E, which is an elliptic curve of conductor N equals to Mn prime, where M is the product of the all primes P dividing N, such that the valuation of P at N is 1 and the valuation of P at the determinant of the curve is divides L. So if then E is modular and the residual L-adic residual Gauss representation is irreducible, then the L-adic Gauss representation of E is modular of way2 and level N prime. So actually they are similar because you can see from the condition of the first one, its conductor is an L, and after that, the new form G, the conductor of new form G is N, and here is the same. So here, then we got the corollary that is the free curve is not modular. The essence of the Ribet theorems less that for the local property of the Gauss representation, just like we talked before, unramified and flat, it forces the modular form to exist at a lower level, and this constraint is so strong that it can't freely adhere to a high-level modular form. For the free curve, the residual L-adic Gauss representation is flat P, so which forces it to correspond to a low-level modular form. but the space of this low-level modular form is empty, thus leading to a contradiction. So finally, let's see the proof of the FLT. The statement states that for any integer n greater than or equal to 3, the x to the power of n and plus y to the power of n equals 0, equals to z to the power of n has no solution in positive integers x, y, z. By doing a transformation, we can move the z to the power p to the left of the equation and substitute minus z to z. So we got the Fermat equation is x to the power p plus y to the power p plus z to the power p. And for the cases when n equals 3 and n equals 4, there are mathematicians proving, and there were mathematicians proving it. So we are only left to prove that for a prime p greater or equal to 5, and ABC is integer a to the power p plus b to the power p plus c to the power p equals 0, implies ABC is equal to 0. This is the ABC equals to 0 means this is the trivial solution. So we prove it by contradiction. We suppose ABC is not equal to 0, and assume further A is congruent to -1 modulo 4, and B is an even number with a free curve constructed as follows. Let the Galois representation rho E0 be the associated Galois representation. By the previous proposition, it is semi-stable. The free curve is semi-stable and has conductor n, which is the product of L dividing the ABC. By the Wiles theorem, E0 is modular, and there exists way2 new form f of conductor n associated to E0. Particularly, we have the Galois representation of f and E0 is equal. So then, according to the theorem in the Galois representation, we find that the rho E0 is absolutely irreducible and unramified outside 2p and flat at p. Applying the Ribet theorem, we divided by 2. We conclude that there is we divided by p, and we conclude that there is a way2 new form G of conductor 2, such that the residual of Galois representation of E is isomorphic to the Galois representation of G. However, the dimension of the S2 gamma 02, which we talked before, is absolutely 0. So this leads to a contradiction. So Fermat's theorem is proved. Okay, that's all for my part. Thank you.
How do you go from
Here?
Yeah. How do you find it?
Oh, no. Okay. Let's see. Oh, we just use this definition. It's okay. Actually, I have no ideas, but based on from what I've seen in the thesis, this state it is the associated Gauss representation.
Something extra or Pause. Can you go back to the definition?
Okay.
Yeah, so representation comes with map drawn like the, so you already pick your vector space to be ZP, right? Yeah, to be ZP, so that's the thing you pick. And then you need to tell us what is row. You haven't defined the row yet. I think it's not general, right? I think, should this be it should be the specific row, right? General. I mean, can you go back to the last book? Go back to after you use oh. Yeah, this part there. Left row be a function. So is this proposition using the Galois representation? Which part uses Galois representation?
The first line.
This one.
Yeah, the first line.
Yeah, so this row is random row. A random row or fixed row?
Not a random row.
What I mean the question is what representation? What kind of representation? Any representation? Any
A specific. Yeah.
so I think we need
Yeah.
I think yeah, you should define it what this row is. Other question. Yeah, this is it's 16. 16.
Systems in English. Here. This system.
What?
Inertial subgroup. Inner subgroup is a normal subgroup of the decomposition group. Because it will go further to the group theory, so I skip that. But you just know it is a normal subgroup, and the quotient group determined by it is isomorphic to a residual Gauss group. Yeah, over a residual field. Is the quotient group is a residual field portion by the initial group, and it is isomorphic to a corresponding Galois group.
Take group portion by the subgroup again. Isomorphic to
Isomorphic to a Galois group. Yeah. Sorry?
Can you write down the definition also? I mean, like, in order to if you want to define it.
It's the yeah, I don't know.
Don't know.
Yeah, I didn't look up to.
Okay, you try look it up and then put it to your.
Okay. What? It's just a normal group, subgroup. Yeah, yeah. Yeah.
It sounds really like that. And use normal circle. It's the initial circle.
Remain what?
It's the initial circle. Why do you keep that actually?
Sorry, I didn't hear you clearly.
Have only one initial circle or more than one?
I guess it's the only one.
Guess.
Yeah.
Okay.
Okay, can we invite all the group member here? Yeah, any last question? Hey, 静怡跑很快啊，静怡。静怡 stay here please. Okay. Any other question, last question for the group? Hey, you guys prove a very remarkable theorem. But since I know reaction, you guys are very tame. Galois representation, modular form. So we proved Fermat last theorem. No excitement, no anything. Huh? Every tired. Huh? Any last question? No? Okay, if not, we will thank them again. Okay, so we will resume after 10 minutes. Okay, 4:17. Yeah. Okay, we will resume later. Yeah. You guys want to take a photo with your slide? Or take with your modular form. Where's your modular form? This one. This page. This one? Okay. Okay, okay. Huh? Yeah, we have a break now. Break until 4:07. 踩到呗，我就不踩它，不是哦，那个是见不见的，等下我可以再开放。OK OK OK， 好，可以了。
那个准备我的表哥，
OK，
表哥后面还有个准备。
哦，太惨了哎。
多一个可能。